Hello students, welcome back to this lecture series on VLSI design KEC 072. This is lecture number 13. I am Dr. Raman Kapoor, Associate Professor at AVS Engineering College. The topic which I want to discuss today is a continuation of our previous few lectures based on dynamic CMOS logic design. So, we are going to discuss what is known as np-CMOS logic and a non-overlapping clock design. Okay. So, till now we have seen quite a few design methodologies. We have seen static CMOS design, where there is no role of a clock, the signal remains as long as they are there, the output gets keep on calculating. It offers very good noise immunity, it is very robust, but then it uses a lot of transistors. Okay. So, scalability, increasing complexity is an issue. Then we moved on to dynamic CMOS logic design, which allows less number of transistors for the same logic, but is prone to things like noise, charge sharing, charge leakage. And a major issue is what is known as cascading. Okay. So, when you connect two circuits together in series, charge loss takes place. One solution to that we saw was known as domino logic, which we have discussed in the previous lecture. Before we move forward, there is one thing I want to discuss. Whatever logic design scheme we use, whatever methodology we use, there is something which is common to every design. That being that every CMOS logic design, the C in CMOS stands for complementary. Okay. The two building blocks are your N type MOSFET and a P type MOSFET. Largely we focus on N channel MOSFET because electrons tend to have more mobility as compared with holes. So, N channel devices tend to attract more attention as compared with P channel devices. But if you implement a logic only using N type devices, it will work in many conditions, but there may be certain condition where there might be issues related to signal integrity, signal strength, okay, the effect of noise, because an N channel device is going to have a positive threshold voltage. So, some amount of energy is always lost in turning it on. To pass a logic 1 through an NMOS transistor will require a finite amount of positive voltage, it is so called threshold voltage. P channel devices on the other hand, they work on negative threshold voltages. So, they can be considered as easy to pass a logic 0. Okay. So, for all these things, the complementary nature of N channel and P channel devices is what is generally used, or we can say exploited, to produce logic design circuits. Whether it was static CMOS, dynamic CMOS or domino logic design, all of these have used the complementary nature of N type devices and P type devices. There are certain cases where N type devices are very useful, but for those situations or input conditions when the N type devices produce a weak output, this is where P type devices can be used. So, one such technique which we are going to discuss today is what is known as np-CMOS technique. Okay. The aim of studying this technique is same as why we studied the domino logic circuit design. Okay. We wanted to solve the problem of cascading in a dynamic circuit. So, we used domino logic. We are again using another alternative which is known as np-CMOS. It is sometimes also called np domino logic also. Okay. This is used again to solve the problem of cascading. Okay. The problem of cascading is how effectively the problem of cascading, the solution to that problem lies on the fact how well you can connect one stage to another, or how well you can isolate the signal from one stage to spilling on to the next stage. Okay. Either in domino logic we used an alternative of using an inverter, how you connect the output of stage 1 to input of stage 2. There are other techniques where instead of connection we are focusing more on isolation, how to isolate the signal, the output of preceding stage from the input of the successive stage. Okay. So, let us discuss about np-CMOS technique. It largely uses two elements, one is what is known as N block or N tree, another is p block or p tree. As the name suggests, n block is going to consist of NMOS transistors and p block is going to have p channel MOSFETs. This is how the general structure looks like. Okay. So, if we start from the leftmost side of your slide, the primary inputs are applied to stage number 1. Okay. These are your initial primary inputs. You apply them to a pull down network consisting of NMOS transistors. Okay. So, you can have n number of inputs and then you are going to have n number of MOSFETs. They can be connected in series, in parallel, some in series, some in parallel, depending upon what logic you are trying to implement. Okay. The more complex Boolean expression or logic you are trying to implement, it is accordingly going to increase the circuit design complexity and the number of transistors required. In addition, the clock of your pre-charge transistor is connected to the gate of PMOS. Same clock is used for the gate terminal of the evaluation transistor. Okay. So, till now it is largely like a dynamic CMOS circuit only. You have a pre-charge transistor, you have an evaluation transistor and you have your logic block consisting only of NMOS transistor, only the pull down network which does the conditional evaluation. How you connect this circuit further? The output here, let us call it C1, okay. This is, say let us call it C1, load capacitor C1, that is the output of your stage number 1. This output is connected to one of the input of the PMOS block of in the second stage. Okay. So, this is stage number 1, this is stage number 2. Okay. The output of stage 1, there is no inverter in the middle, nothing, no other circuitry. It is directly being connected to one of the input of the pull up network which is consisting of PMOS transistors. Okay. So, here if it is visible, you can say it is written F bar here, which means it is implementing inverting logic. There is an F here which means it is implementing non inverting logic. Okay. The other inputs, the remaining inputs are applied here to the PMOS block or the P tree or the pull up network. Okay. So, you have one pull down network here, inputs being applied to it, some output is generated after evaluation, logic 0 or logic 1, that is applied to one of the input of a PMOS block, a pull up network, and all other inputs are there. Okay. Now, similarly, the output of this again goes to the next NMOS block and other inputs are applied. The output of this stage goes to one of the input of the PMOS block and all other inputs are applied. The only difference is that how it uses the complementary nature of P and N block is that this stage 1, which is known as N block or N tree, is working when clock is high, okay, and this is working when clock is low. Right. So, when clock is 0, suppose when clock is 0, C1 gets charged, okay, but this PMOS block is not working. Okay. So, when because this is operating on clock bar, complementary clock. So, when clock is 0, this becomes 1. So, this is not charging, this part is not charging. C1 is getting charged to VDD, and when clock goes to 1, this evaluation transistor turns on, whatever input is being applied here, conditional evaluation is done and the output is updated. That output is now transmitted to this PMOS block. At this stage clock is 1, right, which means clock bar is 0. So, this NMOS is now off, okay, and this PMOS is now on. Because this being on, there is a path here to VDD, whatever output is coming here and this is coming here and this is coming here, and this being off, there is no evaluation here. So, whatever is being charged in stage 1 cannot affect stage 2, whatever is happening in stage 2 cannot affect stage 3 and so on. So, this is how instead of connecting a cascade connection, right, you are basically isolating successive stages, the output of successive stages from each other. So, this is how you are basically maintaining signal integrity and not allowing the charge to decay. Right. In the next cycle, when clock is now 0, this clock bar goes 1, this PMOS is disconnected here in the second stage, this NMOS turns on. Okay. So, at this point, depending upon what you have here and the inputs, some output is transmitted. Okay. So, the pre-charge and evaluation of each stage is happening alternatively. One is in pre-charge, another is evaluating, when another is pre-charging, the next stage is evaluating and so on. Okay. So, this way they are not together charging or discharging, whatever is being transmitted from stage 1 is saved, it is isolated from next stage. So, the high output of stage number 1 does not affect whatever is happening at stage number 2, and this is here you take the output of stage 2, let us call it C2, capacitor C2, okay, and so on. This will be capacitor C3 and this is C4. Okay. So, C1, C3, C5, C7 and so on, they are the output load capacitors of stage number of NMOS tree or NMOS stage. Okay. C2, C4, C6, C8 so on, they are the outputs or load capacitors of your PMOS block. Okay. The NMOS is driving your PMOS block, the output is one of the input to the PMOS block. Okay. So, that decides what logic is going to go through. Okay. So, this is how you are basically cascading this output to this stage, the output of this stage to this stage, the output of this stage to this stage. Okay. Clock is high stage, your NMOS stage is doing your evaluation. When clock goes low, the NMOS in stage 2 is doing evaluation and so on, right. And when clock is 1, for the odd stages, the PMOS is charging, right. Here when clock was 1, this was off, this was on. When clock is 0, this starts charging, okay, and this starts evaluating, right. So, this is how an np-CMOS logic circuit works. It uses the complementary property of both n type and p type, and it aims at solving the problem of cascading. If you compare it with domino logic, it does not require an additional inverter, no extra circuitry is required. Okay. The only thing is that you have different blocks of transistors, and in a simple dynamic circuit you only have NMOS or pull down network which does your conditional evaluation. Here in successive stages and alternatively you also have a pull up network which is helping in evaluation part. Okay. So, that was a general structure. This is one of the circuit which you can call it a small circuit. So, here you have again this clock here, okay. Then a pull down network, output connected here and pull up network. If you want to connect to some other n type blocks or other p type blocks, you can use an inverter here. Okay. So, that is why in some cases it is also known as NP domino logic as well. Right. So, in a p type or tree logic gate, PMOS devices are used, okay, as pull up network like we do normally, including a PMOS evaluation transistor also. So, here at this point evaluation is also being done by p type transistor. So, we are taking the advantages or the complementary nature of both n type and p type. The NMOS pre-discharge transistor drives the output low during pre-charge, and the output conditionally makes a 0 to 1 transition during evaluation depending on what logic you are implementing. Okay. It exploits the duality or complementary nature of n and p type devices, thus it is helping you eliminate the cascading problem. If an n logic or n tree is triggered by clock, the p type block is triggered by complementary clock, which we have just seen in the general structure and we have seen in the circuit diagram. During the pre-charge phase, when clock is 0, the output of the N network or N tree out 1 is charged to VDD, while the output of PT grade out 2 is pre-discharged to 0 volt. Okay. So, this is a brief summary again from a circuit point of view of how np-CMOS logic works. Since the N type gate connects PMOS pull up devices, the pull up network of the P tree is turned off at that time, and during evaluation the output of the N tree gate can only make a 1 to 0 transition, okay, conditionally turning on some transistor in the P type network. That basically depends what logic you are implementing. This basically ensures that you have isolated successive stages and there is no charge loss due to discharge. Okay. And similar N tree blocks can follow P type gates without any problem, as input to the N gates are pre-charged to 0. So, this was how np-CMOS logic works. In addition to domino logic, with an added advantage that no extra inverter between successive stages is required, np-CMOS logic tries to solve the problem of cascading. Now, let us see another different type of an approach, okay, not from the circuit point of view, not from the connection point of view, but from the clock's point of view. There is something which is known as an overlapping clock and a non-overlapping clock. Okay. Let us see, you have two clocking signals. One is your clock signal and another is its complement. Okay. So, one of them is high, at that point another is low. When this is low, this is high, this is high, this is low. These you can call it as in this kind of a scenario, if you use a circuit which uses both complementary and non-complementary clock, you would assume or expect one to be 1 and another to be 0. So, if you have a clock signal, pass it through an inverter and get clock complementary signal, right. But every inverter is going to have some kind of a delay. So, at some point of time you might see that both the complementary signals are either 1 or 0, okay, which is not allowed. This is known as clock skew, and in some cases when the output does not follow the changes in clock signal, that is also referred as clock skew. Okay. The clocks can either be overlapping or non-overlapping. We are trying to use what is known as a non-overlapping clocking scheme, which basically says that any two clocking signals, if you are comparing two clocking signals, you can compare more than two also. If you are comparing two clocking signals, both of them should not be equal to 1 at any instant of time. Okay. So, both of them should not be high or logic 1 at any given point of time. Both can be 0, one can be 1, another can be 0, vice versa, but they both cannot be 1. So, if I pass these two signals through an AND gate, I should always get a 0 at the output. Okay. This is particularly useful in a transmission gate arrangement. So, in a two phase non-overlapping clocking signal, that is also another way of solving the problem of cascading. You would use NMOS switches or TG switches. TG means transmission gate, okay, which is a parallel connection of a PMOS and an NMOS. One is driven by clock complementary signal, another by clock. So, at any point of time at least one is on. When clock is 1, okay, the NMOS is on and PMOS is also on, because it is running on clock complementary, right. In that case, both signals 0 or 1 are passed through with same strength. Each transmission gate stage or each stage consists of a basic dynamic logic circuit and some input switches. Those switches are going to be from transmission gate only. It is often called phi subscript I logic, where I is an integer. If this I is equal to 2, you are looking at a two phase non-overlapping clocking scheme. Okay. This is how this arrangement is going to work. This is the symbol of a transmission gate. So, this is a transmission gate. So, you can see there is a bubble here, which means this is your PMOS end, and there is no bubble here, this is your NMOS end. NMOS works on clock, PMOS works on clock complementary. If clock is 1, this works, in that case this goes to 0. So, this also works. When clock is 0, this is off and this is also off. So, this is like a switch 0 or 1. When clock is 0, NMOS is off and PMOS is also off, because it is working on complementary clock, right. And when clock is high, logic 1, NMOS turns on, it passes some signals very easily, and PMOS network is also on because it is working on clock complementary. Okay. So, all type of signals are passed with equal good strength, that is how a transmission gate works as a switch. So, you use TG1 here, say this is transmission gate 1 and this is transmission gate 2. So, this is switch 1 and this is switch 2. Again what you are basically doing is you are isolating successive stages from each other. When this switch is off, stage 1 and stage 2, by off I mean when switch is open. Okay. When clock is low, this NMOS and PMOS both will be off, right. In that case stage 1 is isolated from stage number 2, right. See the signal phi 1 and phi 2 here. When phi 1 is high, you are doing pre-charging of this end. Okay. So, you pre-charge phi 1 logic and latch this phi 2 data, this data is stored here. Either way, when phi 2 is 1, you are pre-charging this stage and whatever is here is being latched. Okay. So, when this is this left side, this stage 1 is pre-charging, data is being latched on in stage 2. When stage 2 is pre-charging, whatever is at the input is being latched on stage number 1. So, you have one phi 1 logic block driven by clock signal phi 1, okay, followed by another stage, suppose stage number 2, which is known as phi 2 stage, which has another transmission gate and another set of logic condition, right, but it has a different clock. These stages are not sharing the same clock. You have one clock signal phi 1 and you have another clock signal phi 2. Phi 1 goes high, switch 1 is closed, whatever input is being applied, it is being passed on. So, say input is anyways there. So, when phi 1 is high, you get some signal here, say logic 1, this test, this is off here, okay, and this is on here. So, when phi 1 is 1, this is on and this is off. So, this is charging, okay. And as I said, this is a non overlapping clocking scheme. Phi 1 and phi 2 together can never be equal to 1. This is what a non overlapping clocking scheme means. So, in this clocking diagram also, timing diagram, phi 1 and phi 2, they can be 0 at the same time, they can be different, one can be 0, another can be 1 and vice versa, but both cannot be 1 at the same time. If they are both 1 at the same time, you are going to see pre-charging together in both the stages. That is something which we do not want, that is not going to solve the problem of cascading. Okay. So, when phi 1 is 1, phi 2 is definitely going to be 0, this switch is closed, pre-charging is taking place. When this phi 1 goes to 0, when this goes to 0, this becomes off and this becomes on. Okay. At this point, you are going to have logic 1 here. So, this is going to be on and this is going to be off. Okay. So, here pre-charging takes place now and whatever data was here, that is being evaluated and that is being latched at this point output, but that is not being transferred as yet because the switch is open till now. And when phi 2 again goes high, okay, when you again this switch goes on, or this switch gets closed, this becomes open, this has nothing to do, and then data gets latched onto here and this starts to charge. So, when one stage is pre-charging, another is testing or latching or evaluating. When the first stage is evaluating, another stage is getting pre-charged or getting ready. The only condition is that the clocks are separate, each stage requires different clock, that from the design aspect might require some extra circuitry, okay, but it solves the problem of cascading in an efficient manner. Both the clocks should not be 1 at the same time, they can be 0 together, but if one is high another has to be low, both cannot be high at the same time, such that the product, the AND operation of these two signals should always be 0. In that case, whatever you have evaluated, suppose in stage 1 gets latched onto it while stage 2 is pre-charging. When pre-charging ends at stage 2, stage 1 say starts to pre-charge and stage 2 starts to evaluate, okay, and then that data is latched onto the next stage. So, you are isolating stages from each other and you are latching data in stages, might reduce speed a little bit, but signal integrity is maintained. Okay. So, this is known as two phase non overlapping clocking scheme. In addition to domino logic or np-CMOS logic, this is another way of solving the problem of cascading in dynamic CMOS devices. Okay. So, with this I come to the end of this lecture. We are again going to continue with the syllabus, whatever is our next topic. Thank you.